Can you hear me fine? Hopefully, yeah. Okay, great. Hi, I'm Noah, and today I will be telling you about something very, very useful that we created in practice, Bartosz Barikowski and I at Hacken during a very, very challenging audit, and that has, you know, had a little bit of a life of its own since then. So a little bit about me, ex-Hacken. I pen tested a ton of projects and I got lucky because no hacks. Other than that, I really like testing. I do fuzzing for L1s and stuff like that. Outside of the CS career, I've actually been in physics a lot. I've mentored medal-winning students, and if anyone wants to sponsor the Croatian, physics tournament team, we would be very, very glad to take about 20K a year, and you get to have it. You get all the medals. Okay. Other than that, I'm the active contributor to many open source projects and the maintainer of WasmCov. By the way, I like public transport, and Belgrade is pretty good. Pretty regular buses, pretty regular trams. It's nice. It's bikeable as well. So let's start. We'll start with the intro, the problem with WASM coverage. Then we'll talk about how to get it fixed, and we'll have a little demo and some QA time later. So first, what do all of these have in common? Okay, so we have Polkadot, Cosm, WASM, and Near. They're all Rust-based. They're all sort of layer 1 or layer 1 kits. They all use WASM, but what they really have in common is that you can write code, you can write a smart contract, and you can test it, and you can get, using standard Rust coverage tooling, 100% test coverage. And then you can put that code on the blockchain, and you can try to use it, and it won't work. It just won't work whatsoever. And the reason it won't work is, and now let's get to a specific example, is because, for example, on Near protocol, to create, authorized functions, like in Solidity only owner, the equivalent of that, you need to use like the main account key. And to use the main account key, you need to attach one yoke to Near, which is like, equivalent to a way to the transaction. And to be able to attach one yoke to Near to a transaction, you have a payable macro. And a payable macro only gets triggered when compiling to WASM32, okay? But your tests, the tests that you were writing, they were never running on the Near VM. They were running on your local runtime using the standard Rust test runners, which were compiling to x86, which were not triggering any of the macros because these are all like WASM bindgen macros that only trigger for specific targets. So your test suite lied to you. You didn't know it. You just spent some time deploying code. Of course, luckily it's in a cheaper network, so it's okay-ish. But you create something broken and you had no idea. You had no way to even have an idea without literally manually testing it. Because coverage for WASM modules in integration tests is not possible. There wouldn't be a report telling you, hey, by the way, you missed this line of code where you missed this function, and that means you would never really test the function in an integration test where you would catch that maybe the payable macro is missing. And this is a real world thing. So this happened to the only big project on Near, Sweatcoin, and they learned. They were like, yeah, we're gonna add integration tests now. I found this issue right here, and what I was thinking after this was like, okay, but I had to find this issue manually. Actually, we didn't have WasmCov at that point. This is just pretty much when I figured out how broken this is. And I found this manual and I was like, okay, I don't like doing stuff manually. I want this to never happen again to anyone and for it to be easy to find bugs like these. So how do you achieve that? How do you make it easy to resolve situations like this? Well, all you need is test coverage, right? All you need is actual functioning test coverage. I just told you a minute ago. But why is there no test coverage? These blockchain projects have been existing for many, many years, and they have a ton of money locked in them. yet the developer tooling is insanely bad. And the reason is that it's not that easy. There's really not that many projects realistically focusing on code quality, but B, doing stuff like this, it requires a certain type of person that has a particular set of skills and that is willing to dig into compiler internals to solve the issue, because anyone else will just, throw more QA at it and it will be fine. It's just going to cost you one QA person clicking a little bit and they'll hopefully find stuff like this, right? But if you want to automate it, if you want to make sure everything is fine in an automatic machine-like way, then you're going to need to dig through compiler internals, something most of you probably do not do regularly, except that now we're going to do it. So a little bit about Rust and how Rust and actually many other languages work. We have LLVM, okay? Low-level virtual machine, which is not what it means anymore. It's very, very old. It's like a front end for programming languages. In short, in the olden days, okay, really olden days, like 70s, 80s, and I'm talking from experience, because I've lived in. If you were, for example, creating the PowerPC architecture, you would also write a C compiler for that architecture, and you write a lot of this like compiler tooling that goes straight from C to the architecture. Back then there was also like no general standardization, so you had also C95, C98, the Microsoft C, blah blah blah, like all the non-standard standards. Then LLVM came along and they were like, you know what? Let's make this a little bit easier. Let's make it so that we just have, instead of having for each language like a full route from the language to each architecture, let's just make it so that we go from a language to an intermediate representation and from the IR to an architecture. So that means if you were creating a new language, let's call it D, and actually D is a language and it's sort of pretty cool. All you need to do for it to support all the architectures is to just add a pathway from that to the IR. And the same thing, if you're, for example, creating a new thing, let's call it reduced instruction set computing, because that seems like a cool name, right? All you need to do is make a new pathway from the IR to this cool new architecture, right? That's so much more efficient. And you reduce the complexity from like n squared to just n plus m, right? So it's easier. And LLVM is pretty old. It's a pretty big foundation. It's a bit slow moving, but they do have some coverage tooling. I think a lot of people have heard of LLVMCov here. At least this is Rust Summit, so at least through Taiki's Cargo LLVMCov package that replaces Tarpaulin and is sort of, well, it's the better solution. It's honestly, I only started using Rust once coverage stabilized using LLVMCov. Before that, I was like, I ain't using this because I love coverage. And this tool works. It works for a lot of stuff. It just doesn't work for WASM. Why it doesn't work for WASM is a story of WASM, which, you know what? WASM recently got support for file writes, like 2 months ago. The standard was written. And now a big organization like LLVM can finally write support for that part, because before that they wouldn't do it, because why would we do it? It's not standardized. We don't want to rewrite it, right? We don't want to follow some random proprietary implementation of WASM. So yeah, there's progress there. But it doesn't work for WASM. And that's where we get to the inception of WasmCov. How do we solve this problem that doesn't work for WASM? Or rather, why doesn't it work for WASM? And what can we learn here? So the reason this doesn't work for WASM is because there's some garbling in this step, okay? Between the IR, which is fine, and the WASM compile. There's some garbling where the LLVM coverage mapping data is lost, which is what tells you what was this code actually doing, what was this bytecode related to in terms of the source code. And once we figured that out, we knew that we had to use something else to get to the coverage. But to get to the coverage, we had a lot of little steps. And being smart, we first took a step back and looked at what is the problem we're actually solving in general. And the problem we're solving in general is getting coverage on a very, very limited virtual machine. So on top of all these like WASM problems and no direct WASM support, we also had another issue that was just that this is actually a no profiler runtime with no file writes. You're not going to be able to write files out of like a custom VM like that. With custom domain specific SDKs, it's going to be tough either way. And we took some inspiration. We realized that a lot of these things would be solved if we just searched for maybe some bare metal libraries that are used to working in, no STD, no profiler runtimes. And thus, we create a little bit of a process. The process was, one, somehow we need to generate code coverage and profiler data in the runtime, despite it being no STD, no profiler. Two, we need to find a way to extract it. So in a, if you were an embedded engineer, you would have like a port somewhere where you're just passing all of that as serial data, because there's no operating system, there's nothing. Step three is unknown unknowns, which we enjoy very much. And step four is generating a human readable coverage report. So let's start with the first step. This is when I joined Rust, when this was no longer a Z flag, okay? Instrument coverage. So that's one thing. And the other thing is we make it a no profiler runtime. And then we can use a really cool tool called WasmCov, which is meant for embedded no STD blah, blah, blah runtimes, which allows you to take this profiler data, which is being generated by the instrumentation, and access it within the program, because otherwise, you just cannot reach it. Because normally, the instrument coverage pipeline, it automatically writes these as profro files. It writes the profiler data out of into some target directory, etc. But we cannot do that here because it's all happening within a VM. So the first step, we're getting coverage instrumentation. It's okay. We just cannot get this coverage data out. Second step, getting the data out. So figure out WasmCov could help us here. Pretty much we add like a utility function. We either patch the VM and we patch the code as well. So we need to patch the code generation pipeline for the whatever. So each blockchain sort of runs on a different thing. Polkadot uses WASMI, Near uses WasmR, and I don't know what all the others use, but each one is a bit different because no standardization, and each one requires a custom patch to their code gen logic and a custom patch to a lot of stuff. But the custom patch is more or less when the VM is about to be killed or whatever, we want to run this. So what this does is it gets the coverage information data into this coverage vector. And then we call a function, which is a function that we need to patch on the VM, that is somehow going to save that data. How do we save this data? Well, depends how friendly the developers of the VM are when it comes to supporting coverage. Because if they're very nice, they may actually help us create a whole nice development patch that allows us to just get the data directly into a file. If they're not very nice, I'm going to be stuck reverse engineering the runtime and trying to figure out how to get the data out through logs or just writing it to storage of the blockchain and then reading that storage, etc. There's a few ways there, but that's pretty much how that part goes. And then once we got the data out, once we got some profro data out, we can try to generate a coverage report. So we go like, LVMCov, show instrument profile coverage. So we put this coverage data. Before that, we do some cleaning. So we merge the data, blah, 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 move it to the right place. But that's easy. And then we, try to run it on our binary. And that's when we find out about this no coverage data thingy. This is the unknown unknown. So what's happening here? In short, the coverage generation doesn't work because a WASM binary doesn't have an LVM cover map section. that is needed to generate the report. But we can dig and we can figure out what happened. And I gave you a little bit of a spoiler. That's because I was reading Dune earlier. So I was really inspired by the whole, you know what, I have a premonition of the rest of this book, and now you're going to read it. And then you're going to read the rest of the book with all the spoilers intact, okay? So I did a bit of that by accident. Not by accident. But how do we fix that? Okay, we dug through the compiler internals, and we figured out that the IR was fine. Okay, and that means, and we figured out that the WASM compilation step is broken, but we figured out that all the other compilation steps work. Like you can compile to, I don't know, x86. So what we did was we cross-compiled the IR. So we put a little flag into the compilation part to emit the IR. We edited the IR, okay, just casually, a little bit. And we actually, for a start, we didn't edit it. We just cross-compiled to x86, okay? Cross-compiled to x86 and trying to run the previous command, but here we have like an object file, actually worked. You could get like a rudimentary coverage report on like the most basic WASM test file. Moving that to a more complex test file, we realized that there are some differences after all, especially in memory management. So, you know, you have grow and shrink memory in WASM, while x86 is going to have pointers and allocators working differently in terms of like, you know, bindings and how the VM is written. So we just needed to stop this. So we wrote a little script that's going to just go through the IR, and everywhere where we're invoking WASM custom stuff, WASM specific stuff that would break the compilation, we just remove it. We replaced it with unreachable or something. And now coverage can be generated using this workaround. And there's a bit more detail. If you want to read about it, this is like the workaround in depth. But actually there's more. So as I was mentioning earlier, to get all of this working, we had to modify the VM. We had to make sure a lot of this random tooling was installed. We had some script that was modifying intermediate representation. That's like a random step. We had all the flags that needed to be managed. We had all the management of, you know, the cross compilation and the modified IR and how we were processing that. And there's a solid like 20, 30 commands being ran there. And I was like, okay, we managed to get this working once for one project, Sweatcoin at the time, but I want this to work like in general, because even moving this from just Sweatcoin to near protocol in general seemed like maybe a little bit of a daunting task based on like the hard-coded complexity of all the commands. So I was like, you know what, I want to make this nice. When I was younger, 2 years younger exactly, I read a UX book too, actually. Don't Make Me Think and The Design of Everyday Things, and I was very, very inspired. And I was like, you know what, I want to make this very, very easy to use. I want to make this stupid easy to use. And pretty much I went and I pushed to implement all of the steps that we had into like a nice flow, so it's all sort of automatic. And that the only thing that you really need to do is add some of the patching to the VM that's gonna put the prof rod to a consistent place. And that's pretty much what I did. So this is published as a Rust library and as a command line tool that you can use. And you pretty much run cargo WasmCov setup, or you run WasmCov setup from the called as a library. You build your contracts, you run your external tests, however you want, that are using the built WASM binaries, and then you just run finalize. And these steps automate away the regex for modifying the IR, the compilation, the modifying of everything, the moving around of files, because you know you may be using these compiled contracts somewhere, and you want to make sure that you're using the unmodified ones and not the modified ones. You know, so there's a lot of little tricky things. And I think this is pretty easy to use. Yeah, it's been a bit. This has been implemented in a few places. I think this is the demo now. Yeah. you can see pretty much how easy it is. This is the Radix implementation. And what I like about video demos is that they don't work when downloaded. Shit. Help. Okay, so imam video demo. Aha. Ne radi.
Because it's
Oh. Yes.
sure.
Maybe a bit low quality. Okay, so this is like the Radix demo. Nice thing about video demos is that you can cut out the compilation part, which is like 2 minutes, and you get a coverage report generated very, very quickly, just a single command, nicely integrated. The coverage report is a bit different than what you may be used to, but it has the function line and region coverage as a standard for LLVM reports, and it includes dependencies. That's what I meant by unusual, but you can look at your target files, you can remove the dependencies later and clean it up. And once you open it, you can check all the lines that are covered, etc., check all your functions, blah, blah, blah. Like, it's what you would expect from a coverage report. It's nothing special, but it works, right? And this didn't exist before. And since, okay, where is the, is it here? And how do I go back to full screen? Help again.
Yes. Do you see maybe this?
Okay. And since this was, created, I've been following the progress of other people using this because I put it on the internet on GitHub publicly for a reason, and that's that I actually want people to use this for free and maybe, pay me a little bit for some implementation help if they really want to. And since then, I've seen this implemented in Wasm Bioengine and WasmPack. So there's progress on getting that directly on that level. Near Protocol and Radix have implementations because they like to support developers. And most recently, I'm really happy for this. There's a movement to replace Kubernetes and Docker with Wasm, because when you have Docker containers, they are huge. They can be like a gigabyte if you're not very optimal, or 3. And they take a while to boot up because they're pretty much a good bit of a Linux executable. But with Wasm, you can have a sort of hot machine running, and then you just feed the binaries as input, and it's much, much faster to boot up. Instead of like up to seconds, it can be milliseconds to start running, which makes it very viable for serverless functions and serverless workers, or for Cloudflare workers. And I've noticed that the Cloudflare workers official repo is actually now reading our method implementation guidelines and referencing some of that and implementing it. So it's pretty nice to have like a big name that likes coverage. So yeah, that's it. Thank you everyone for listening, and let's go on to the Q&A. Any questions? By the way, like, I hope you understood everything, because like the original version of this presentation, I was just waving my hands around for the whole like compiler internals part, because originally I held this in front of a security engineer audience, and everyone understood everything and I could wave my hands about. But when I tried to move this to more mainstream conferences, it was really tough because, well, not everyone digs through compiler internals daily. That's pretty much it. Anyone that, oh yeah, I forgot the poll question. That's because I didn't have speaker notes. Who here has like proper coverage? Who here aims for a good 100%? One. In Rust? Okay, some other fun questions. Who uses mutation testing? One, the same one, and 2, okay. What about fuzzers? who here can, what do you use? Just cargo fuzz, or do you use, do you go directly with AFL? Aha, so like Echidna. Ah, okay. Okay, that's it. If there are no more questions, thank you everyone for listening. And yeah, feel free to approach me later.